SwayamPrabha. Digital India. Educated India.
So, last time we considered what will be the general velocity field if a rate of expansion is specified everywhere or a vorticity is specified everywhere, and then as a specific example we consider a singularity in the distribution of rate of expansion, where the rate of expansion is infinite at a point, but everywhere else it is 0. And we approached this by considering a large rate of expansion, which mathematically can be described by a step, a peak at a small region, and then we approached this small region to a point by which we obtained a point source, and we derived the potential function phi e and the velocity distribution that is obtained by this point source, which is a singularity in the rate of expansion distribution, because in this case there is a rate of expansion of infinite amount at one point and everywhere else it is 0, or if not 0 there might be some other values, but which can be additive, which can be added. Also, if you look to this expression for phi e and the u that we obtained, the velocity that we obtained, that both approaches to a very large value as r approaches 0. Also, you will calculate, this is point source, what we had phi e is minus m by 4 pi r and u e as m by 4 pi. Okay. To give the direction, we wrote it r by r cube. That is m by 4 pi r square in the direction of r. The velocity, as you can see clearly, is decreases with inverse square of r, and as r approaches 0, the velocity becomes extremely large, and at r equal to 0, neither this potential nor the velocity is defined. This is why these are called singularity. Okay. If we consider any closed surface enclosing the point at which the source is located, then the flux of volume across that closed surface is m, which is called the strength of the source. Okay, we will later on see that a single source, a single point source is usually not created by any dynamical effect due to certain forces. Usually, wherever there is a source type of situation, this is due to some external reason, that is either you inject fluid at certain point or you suck in certain amount of fluid at some point, that gives rise to near about a source type of situation. Otherwise, just by the application of the forces that usually exerted on a fluid, this type of point source situation usually does not arise. If the strength is taken minus m, then the singularity is called point sink. If m is positive, it is source; if m is negative, it is called sink. M is negative, it is point sink. Later on, we will see that the utility of these point source or these is constructing more important, more interesting flow field. On its own, point source really is not very important, but its main importance lies in the fact that it can represent along with others a much more interesting and often some practical flow fields, but of course, we will come to those later. The next singularity that we would like to consider is a combination of a point source and point sink placed a delta x distance away. Both the point sink and the point source have same strength. Let us consider that sink source has a strength of m, the sink has a strength of minus m, and they are separated by a distance delta x. Now, think about that we are decreasing this separating distance delta x and simultaneously increasing this m. The strength is being increased while the separation is being decreased in such a way that the product always remain constant, that is m into delta x, that remain constant. Say, let us consider this is the sink, this is the source, okay. This distance is, okay, we will call it delta x prime. This point is say x minus x prime minus half delta x prime, and this point is x prime plus half delta x prime. Okay. These are all vector. Okay. That means, it is really the coordinate of the point. As you can see that direction also, this line joining these sink and source is actually called the axis, and this new singularity that now appears is called source doublet or dipole, source doublet or source dipole. Source doublet or source dipole. Now, one thing you can see at this stage itself, that if you now in the limiting case both of them are at point x prime. So, this is a point doublet placed at point x prime. Now, think about any closed surface enclosing this point x prime where the doublet is placed. What will be the volume flux out or the volume outflow through that surface? Obviously, it is 0, because the strength of the source and sink, they cancel each other. So, in this case there is no net volume flow. Now, in this case again the solution phi e and the velocity, that can be very easily obtained by superimposing the potential due to point sink and point source, and then approaching as delta x to 0. So, that phi e, the potential at any point, we will call it potential, we will see why later on. This function phi e what it will be? Is minus 1 by x minus x prime. So, this is x minus x prime minus half delta x prime, the magnitude of it. M by 4 pi r is phi e for point source, minus m by 4 pi r, this is the r. Okay. Okay. Plus the sink one how much is this? How much is this? It's all right, no? And that will be so we can write this as what? Mu by 4 pi sorry This is just to indicate that this function phi for a point doublet is obtained by a gradient of the phi for source. This 1 by r was the phi for source, but in this case now we have a gradient of one by r. Now, to obtain the velocity field, gradient of phi is the velocity field. Will be how much? 1 by 4 pi gradient of mu, okay, all are with respect to this x. Can you evaluate it? What will be gradient of 1 by r? What is gradient of 1 by r? Minus 1 by r square in the direction of r. So, we will write it in this fashion. One more gradient of that. So, this is the velocity field due to the point doublet. This is the velocity field due to the point doublet. The first observation that we can have from here, that in this case the velocity decreases with inverse cube of the distance. Comparing with the source, in case of a source, the velocity was decreasing with inverse square of the distance. In this case, velocity is decreasing with inverse cube of the distance. Also, this velocity field has an axial symmetry about the axis of the doublet, that is in the direction of mu. The velocity field has a symmetry about the direction of mu or about the axis of the doublet. And you can also see that the azimuthal component of this velocity, like say this is the doublet axis, the azimuthal component is this component, that azimuthal component is 0. So, you see that velocity decreases with r to the power minus 3. Velocity is symmetric about the direction of mu since the azimuthal component is 0. So, in the axial plane the velocity is like 2 dimensional, okay. The velocity field is 2 dimensional in any axial plane, and hence we can construct a stream function for it. Using the definition, using that r theta phi coordinate system, considering a r theta phi coordinate system, origin at the location of doublet and theta equal to 0 along doublet axis, that is along the direction of mu. The radial component of velocity is given by 1 by r square sin theta d psi d theta, where psi is the stream function which we have defined earlier. So, in this coordinate system this is what is the, and how can we get u r? U r we can easily obtain as u dot r by r. This u already we have the expression that we have written, that 1 by 4 pi minus mu by r cube plus 3 mu dot r by r to the power 5 r. So, take a dot product with r and tell me how much is this. Or okay, let us write 1 by 4 pi, this r comes here, the first term becomes minus mu dot r by r cube, and the second term becomes 3 mu dot r by r to the power 5 and r dot r, that is r square. Yes, minus mu dot r, minus is there, and the result is how much? One by 2 pi mu dot r by r to the power 4. We can write this further, that 1 by 2 pi mu cos theta by r cube. Okay. Mu dot r is mu r cos theta. So, now we can evaluate what is psi. Gives what? D psi d theta is mu by 2 pi sin theta by sin theta cos theta by r, no. And so psi equal to mu by 4 pi sin square theta by r. The constant of integration can be a function of r and phi, but that we are just taking it for granted. Of course, you can check it that to have the proper tangential velocity, that constant of integration has to be 0. The velocity you have already found. So, we can find what is the radial velocity as well as what will be the tangential velocity or the transverse velocity, and the transverse velocity, to get that proper transverse velocity, you can see that this constant of integration will be 0. We are not doing it, but if you want you can check it. Now, we can construct similar type of singularities, even more complex or more higher order singularities. As an example, like we placed two sources and then brought them closer, we can do the same thing. We can place two doublet, one of strength mu, the other of strength minus mu, and then can imagine that they are being brought closer and closer, such that the product of that strength and the separating distance, okay, both being vector, it will be a vector product that should remain constant, and we can get what is known as quadrupole. This is dipole and then two dipole, that will make a quadrupole. We can obtain the quadrupole in another manner. Think about a parallelogram of any shape and then place two sources in the opposite corner and to sink on the remaining two opposite corners, and then imagine that this parallelogram is sinking to a point. Again you will get that same doublet, sorry, quadrupole, not dipole, same quadrupole. However, they are very rarely used, this higher order singularity. So, we will not go into that, but we will talk about two more very important singularities in rate of expansion. One is when there is singularity over a line. Initially, you consider a singularity at a point, that the rate of expansion is infinite there, and everywhere else it is either 0 or may have some finite value. It is possible to consider a line at which again there is peak, but peak is not at a point along a line, then it is called a line source. Similarly, we can consider a surface on which there is peak in the singularity distribution. At each and every point on that surface there is peak, which we then call a surface distribution. And as the flux across a closed surface surrounding the point for a point source gives the volume flux, in case of a line also, if we consider the flux for unit length of that line, then that will give the line density of the line source. It is called line density of the strength line source. Similarly, for a surface, if we consider a unit surface area and then flux from that unit surface area is also called the flux density, or in this case surface density of the surface source or strength of the surface source. These will be very important and we will come back to them again and again, but right now just consider one line source, and to make it simple, consider this line source, the strength is everywhere constant. It is not necessarily that the strength has to be constant or the line density has to be constant, it is not necessary, but to make it simple we will consider that line density is constant everywhere, and not only that, we will also consider that this line is infinite. And again for simplicity, let us consider that this line is parallel to the z axis and passing through point say x prime y prime. Then so consider a line source with constant line density of strength we will call this again M. Consider it parallel to z axis. Passing through the point x prime y prime and this line is from the line is infinite. Now, to find the velocity due to this line source, what we can do is we can consider a small element of that line of length say delta z prime, then the strength of that small line element is m into delta z prime, and this small line element can be thought of as a point, and we know the velocity distribution for a point source of strength. In this case the strength is m delta z prime. So, knowing the velocity for that, we can now integrate the velocity from minus infinity to plus infinity, that will give us the velocity. So, how much it will be? So, the u component, let us write now in component form, not in the vector form. How much it will be? We will use the same notation u e. Since the m is constant, it will come out of the integration m by 4 pi into what the velocity was m by 4 pi r square in the direction of r. Now, take the x component of that. Or in this way m by 4 pi vector r divided by r cube. Now, take the x component. The x component is simply x minus x prime the x component of that r vector is simply x minus x prime. This x is no longer the vector x. Okay. Please make these differences, because we are using in this case x as simply the one of the coordinate. In the earlier cases, we are using x as the position vector or the point vector. Okay. So, that difference you should remember, where we are using x as simply one of the Cartesian coordinate, or where we are using x as a position vector of a point. And the result will be m by 2 pi x minus x prime by, we will write it as a square. The difference between this r and s, that r is the usual distance between 2 points considering all 3 coordinates, while this s will contain only x and y. This s square that is, it is the perpendicular distance of the point from the line. The perpendicular distance of the point x y from the line source, that is what is this. The second component of the velocity again in that same manner. Now, this velocity field is irrotational, which is quite obvious. We are when we consider this velocity due to rate of expansion, we consider it to be irrotational only. So, since this is irrotational velocity field, this velocity field can be expressed as a gradient of upon a scalar function. So, can you say what will be that function whose gradient has these two components? Can you say what function will have it gradient component given by these two, u e and v e? Yes. Log r. So, this is the gradient of the function log r. Okay, this m by 2 pi of course will remain. So, we can see that the potential function in this case is you may try to find out this potential by integrating the potential due to a point source. Please try it and see what happens. For the velocity, that is what we have done. We have considered the velocity due to a point source and then integrated it. Try it for the potential due to a point source and then integrate it over minus infinity to infinity. You will see that your integration will fail. The integration will diverge, and we will be needing some special technique to complete that integration. Anyway, now let us look to this, an infinite line source whose strength is remaining unchanged in the direction of the line source, in the z direction. The strength is everywhere constant. So, obviously, the velocity field that it will produce will also not change along z. So, what type of flow it is? It is a two dimensional flow, in which case there is no change in along one direction. And what is an infinite line in two dimensional representation? How this line, infinite line from z equal to minus infinity to plus infinity, will be represented in the xy plane point. Okay. So, what is a three dimensional infinite line is basically a two dimensional point. So, this is now can be called as a two dimensional point source. Similarly, we can have two dimensional point doublet also. You may try to construct the two dimensional point doublet. Now, before we move to something else, let us say something about this velocity field. These velocity fields are obviously whatever, either due to point source or point doublet or this infinite line source, which is equivalent to a two dimensional point source, are all irrotational velocity, okay, because from there only we have started. So, the curl of all these velocity field is 0. These velocity fields are irrotational. Now, can you say anything about the streamlines? How will the streamlines look? Say for a point source, how will be the streamlines? Streamlines are line to which the velocity vector is always tangential. So, look to the velocity vector and then think what type of line will be tangential to that. For a point source, what is the direction of the velocity? R. So, radial direction, considering the point is a radial direction, and line tangential to that means radial lines. So, the streamlines are just radial lines from the point source, like this. If this is the point source, sorry, so these are the streamlines for a point source, as simple as that. If it is point sink, it will, the arrow will change its direction, that is all. Knowing this, can you say what will be these streamlines or general shape of the streamlines for a point doublet in any axial plane? In this case, with respect to me, the source is right of me and the sink is left. There will be similar set of lines on the bottom half also. I am showing only one half. Okay. This is symmetric about this line. Only half is shown, the top half, bottom half is not shown. Okay. I have not written that, but it is that. Next, we will consider similar specific examples for vorticity distribution, that is certain singularities in vorticity distribution. However, before we go to that vorticity distribution, let us have some general properties, of course, some simple general properties associated with vorticity. As you have mentioned earlier, that vorticity is a very important quantity, important flow parameter, and you will see in all your aerodynamic courses how important it is and how much insight it gives about the overall flow, and what are its practical usefulness and significance. But at this stage, of course, we are just having only some simple kinematical consideration, and based on that kinematical consideration, let us see what we can find. First of all, you see the vorticity is defined as the curl of the velocity field. Okay, we denoted that part only by u v, but curl of total u is also the same thing, because the other parts will have no curl. Other than u v, there are those part u, e and v which we wrote, they do not have any curl. So, that curl of the total velocity is same as the curl of the only that u v part. Anyway, that really does not matter. Now, see this vorticity is curl of another vector, and it is a mathematical identity. The divergence of a curl is always 0. You can try it. You can just check divergence and curl. So, this implies divergence of omega equal to 0, and right now we will see the significance of this. But before that, let us make a few simple definition. Like streamlines, we had the lines which are always tangential to the velocity vector. Similarly, the lines which are always tangential to the vorticity vector are called vortex lines. Analogous to streamlines, they are also called vortex lines, the lines which are always tangential to the vorticity vector. And of course, by the same method through which we derived the equation for streamlines, if you remember that we made u cross ds as 0, which gives us dx by u equal to dy by v equal to dz by w as the equation of the streamlines. Exactly similar type of equation we can obtain for the vortex lines also. Vortex lines tangential to vorticity vector. That is, if you consider a small segment of that vortex line to be say delta L, and then the vorticity is tangential to that, means omega cross d L is 0, and you can get the equations dx by omega x equal to dy by omega y and so on. Consider a reducible closed curve. We will later on come what is a reducible closed curve, or let us say it at this stage only. The reducible curve is any curve within the fluid which you can shrink to a point without going out of the fluid, or coming to a pure mathematical term, that any curve if you can shrink it to point without going out of the domain of that curve. All curve or all functions are defined over such a domain. Now, if you can shrink that curve, you can deform that curve, you can translate it, you can rotate it, you can move it, anything you can do, but you cannot go out of the domain. And by this process, if you can reduce that curve to a point, then that curve is called a reducible curve. So, in case of a fluid, we will call it any curve which is within the fluid, and then you can shrink it to a point without going out of the fluid, then that curve is called a reducible curve. You can move the curve, you can deform it any way you like, only thing you cannot do is you cannot go out of the fluid, and if you can shrink it to, if you can make it a point, then that curve is reducible. Now, think of such a reducible curve within the fluid, and then if you have the vortex lines through each and every point of that curve, okay, these vortex lines will now form a tubular surface. That tube is called vortex tube. So, all vortex lines passing through a reducible closed curve make a vortex tube. Okay. Let us think about the vortex tube and one of these cross sectional surface. Then the integration of the vorticity over that surface area, over that open surface area, is called the strength of the vortex. Think about that. Okay, this is a vortex tube. Okay. Now think about this surface. Okay. Think about this surface itself. Okay. Then this integration omega dot n dA is called the strength of the vortex tube, strength of the vortex tube. And because of this property, the divergence of omega equal to 0, we can very easily show that the strength of the vortex tube will not change. The vortex tube may change its shape, it may have anything, but the strength will remain same at anywhere, and it is independent of this A that you choose. You may choose this type of A, you may choose this type of A, or any type of area you choose. This vortex strength, the strength of this vortex tube will remain constant, it will not change. And what is the consequence of that or significance of that? That if we have a vortex tube, then vortex tube will never end within the fluid. Because if it ends, means its strength is changing, but it cannot. So, a vortex tube will never end within the fluid, just because of its this definition. We will continue it in next class. The mathematical proof is very simple, just one line mathematical proof, but we will do it next class.